So this will be the first in a series of presentations on moons of the solar system. And, there are over 220 moons around what you might call normal moons or traditional moons around planets, over 400 around other small bodies, Kuiper Belt, TNOs. So out of the close to 700 moons in the solar system, what an honor that Titan gets to go first. I think that's just incredible.
Well, I tell you what it is, Lou. It's to coincide with that lovely James Webb image of Titan released last week or the week before. So we thought Titan would be a good first place to start.
Titan is a great place to start, and we've known this is a great place for many years. And I'm going to walk you through a little bit of the history of Titan exploration, tell you why it's an interesting moon, tell you why we are spending so much of ESA and NASA tax dollars to explore it. So let's get going. I can.
You have control.
I have control. Okay. There we go. So back in the 1600s, the first the first observations of Titan that were realized were by Cassini-Huygens, the Dutch astronomer. And of course, you'll recognize that name because that was what we named the Titan probe that went out to Saturn with the Cassini spacecraft. We named it after Cassini-Huygens. So in this excerpt from his writings, you see Saturn, and you see two stars. You see one in the kind of at the 3 o'clock position and one at the 7 o'clock position. The 3 o'clock position is actually a star. But the one at the 7 o'clock, that was in fact Titan, and he was able to watch that over time, see that it was moving, calculate an orbit, and so he's credited with the discovery of Titan. Then in 1907, with better optics, better telescopes, it was noticed that Saturn has a quality called limb darkening. This is an edge effect that you would see in a body that has an atmosphere. So as you're penetrating down further into the atmosphere, rather than going from deep space to solid surface, you see a gradation of intensities. And this was the first indication that that Titan had an atmosphere. So that alone makes it unique among all other moons of the solar system. Then in the 1940s, Gerard Kuiper, who you will recognize, the Kuiper Airborne Observatory was named after, as well as the Kuiper Belt. He had two big things named after him. I'm still waiting for my first thing, but I know it's coming. And he did some spectroscopic observations of Titan and noticed that there was methane, or as you say in the UK, methane, in the atmosphere. See, I'm getting an error message. Something went wrong. Try reloading the page. Can you see the slide?
We can see the methane slide, yes.
Okay, very good, very good. And we'll continue. So not only does Titan have an atmosphere, now there's methane in the atmosphere. And why is that interesting? For a couple of reasons. It is a biomarker. It can be the result of biological activity, or it can be a resource for microbial, let's say, activity. And also, it shouldn't be there. Methane is very volatile and gets broken apart into its component elements of carbon and hydrogen very easily with ultraviolet radiation. So the fact that it is there on Titan is something that makes Titan even more interesting. So just a few facts about Titan. By the way, this is an image that was taken by the Cassini-Huygens system, visual and infrared mapping spectrometer. This image is not what you would see if you were just kind of flying out there and looked out your window. In this image, we're looking through the very opaque photochemical haze that surrounds Titan down into the surface till we see surface and lower atmospheric features. And you can do this between methane absorption bands in the near infrared, and I'll be showing you other pictures and talking about that quality. But just kind of a Titan 101 here. diameter of 5150 kilometers, surface gravity of 1.35 meters per second squared. Most of the atmosphere is nitrogen, predominantly nitrogen, just like a planet we all know and love, with other hydrocarbons and nitriles. The surface pressure 50% greater than the Earth. And because Titan doesn't have as much gravity, its atmosphere is much more extended than Earth's atmosphere. And then, of course, it has all of these Earth-like features with seasons and rain and clouds and lakes and rivers. And you say, wow, what a great place. But it does all of this at a temperature of 94 Kelvin. For you Fahrenheit friends, it's 290 degrees below 0 Fahrenheit. So all of the fluvial and atmospheric evapotransport mechanisms that go on are not with water. They are with other very interesting hydrocarbons. Just as comparison of Titan to all the other moons of Saturn, clearly the largest moon. Not all the other moons of Saturn, but many of the larger ones. And here's a comparison with just other solar system objects. So you see Earth and Venus on the left. Venus is about 95% the diameter of Earth. Mars is about half the diameter of Earth. And Titan is next and bigger than Mercury. So if Titan was not orbiting Saturn, it would clearly be another planet. But it is orbiting Saturn, so we don't count it. Well, with all of this, these interesting findings, it's no surprise that we've sent a number of missions out to investigate Titan. We sent the Pioneer 11 to Saturn. This is a flyby mission that flew by in '79. Voyagers 1 and 2 flew by in 1980 and '81, again, flyby missions. And then the Cassini spacecraft on its way with gravity assist from Jupiter, orbited Saturn and dropped the Huygens probe into the atmosphere of Titan. Cassini made many, many close encounters with Titan because it's a very important object of interest. And we'll be looking at some of the observations from that in just a moment. So early robotic exploration, Pioneer 11 went to the Saturnian system and took some pictures of Titan. This, it turns out, now I guess I'm not sure if my I have something blocking it here, but this is supposed to be the first robotic spacecraft image of Titan. Of course, this is Saturn here in the middle here with its rings and the shadow of the rings on the beautiful cloud tops of Saturn. But on the bottom, if it's still in frame, is a small dot, and that is the dot, that is the figure of Titan. Wow. Pioneer 11.
We've come a long way, haven't we, Lou?
Oh, we have, as I'll show you in just a second. This was the best image of Titan taken by Pioneer 11 at a distance of 360,000 kilometers.
Wow. Pioneer
11 had a 2-color camera. And again, what we're seeing here is, this is in the visible part of the spectrum. So you're seeing the atmospheric haze that shrouds the entire planet and prevents visible wavelength light from penetrating. Haze, kind of like smog in LA in the summertime, in Los Angeles in the summertime. And this was the best image that Pioneer 11 had, and at the time, the best image that humanity had of Titan.
Didn't learn a lot then.
There was other data taken,
Right.
Spectroscopy of the atmosphere, magnetic field data, and so on, but that was the best visual image. Then in 1977, the 2 Voyager spacecraft were launched on flyby missions to the outer solar system. And over here on the left, we have, I think this is a Voyager 1 image of Titan, much better image. You can see a couple of things here. Of course, the orange-red photochemical haze. By the way, this is produced by the photodissociation of nitrogen and methane and nitrogen and carbon in the atmosphere. And the methane and the nitrogen break into these amazing cacophony of chemicals, which makes Titan even more interesting. You see that the top part of the image here of Titan looks darker than the bottom part. And this is not a solar angle effect. This is actually a compositional and particle size effect, because the atmosphere moves wholesale from one hemisphere to the other every Titan year. And Titan year is roughly 29.5 Earth years, just like Saturn, as it is tidally locked to its planet. You can also see on the top here just a little bit, it looks like it's a little bit not quite round at about your 1 o'clock position. And that is the North Polar Hood, which is a region where chemicals build up in the atmosphere in the winter season for that pole. On the right here, you see some models that we've been able to make of the atmosphere of Titan, showing the photochemical haze, the particulates, and the that are produced, the haze layer further down, and then these hydrocarbons and nitriles kind of precipitate down through the atmosphere and act as nucleation sites for other chemicals to glomp onto, and then they fall out onto the surface. Temperature and pressure of the surface is such that methane can evaporate back up and form methane clouds or methane clouds, and so you have a methane cycle here instead of a water cycle that you'd find on Earth. This is just an example of some of the other kinds of data that we got from the Voyager spacecraft. Obviously, this isn't an image. These squiggly lines come from the IRIS, the infrared interferometer spectrometer on Voyager. And this is from the SATAT link on Voyager 1. Very, very close flyby of Titan.
That's quite a complicated cacophony of chemicals there, isn't it?
It is. It's complicated. It's hard to understand for most people. And so at the daily press conferences, when plus or minus 2 weeks of encounter out at Jet Propulsion Laboratory in Pasadena, California, the imaging team got all of the press and all the oohs and ahs, and we'd show a few of these and nobody cared. But there's an amazing amount of information in here. You can see many of the hydrocarbons and nitriles, HCN, hydrogen cyanide, C2H2, acetylene, CH4, methane, and so on, and ethane, C2H6. Lots and lots of these chemicals that are produced by this prebiotic atmosphere that Titan has. And these images, these little squiggly lines turned out to be very important in understanding the birth and evolution of Titan.
Just out of interest, how does that compare at all with what New Horizons found at Pluto?
In some ways, it does. For example, Pluto has a detached haze layer. We haven't shown that quite yet here. That Titan also has. Pluto's chemistry is different. It's colder, if you can imagine being colder than this. Oops, let's cancel that. But it also has many of the chemicals that we see here. Yes, and I think it deserves its planet status just from that alone.
Indeed.
So we move on, and in 1997, 20 years after Voyager, we launched the Cassini spacecraft with its Huygens Titan probe to Titan. And again, this image here is from the VIMS instrument on Cassini, showing the surface features of Titan. And here we start to see some darker regions. These are lakes on Titan. You can see some of the surface as well as some highlighted parts of the surface, which are likely in this image methane clouds in the lower troposphere of Titan. There's the launch of Cassini. Oops. And here's an artist's rendition of what it would have looked like as Cassini approached the Saturnian system. It released the Huygens probe to fly unaided into the atmosphere of Titan using aerobraking and then eventually a parachute, which, as you might imagine, is very efficient with a very thick atmosphere of Titan to land on the surface.
And just on that point, Lou, somewhere on YouTube, there is a real-time record of Huygens' descent through the atmosphere that you can sit and watch, which is amazing.
Absolutely. And so landing on the surface was amazing, and we got our first glimpses of the surface, which I'll show you in a minute. But for me, who studied the atmosphere of Titan, the progression of Huygens down through the atmosphere, taking measurements of temperature, pressure, composition at each level, was even more important and more interesting. So we got a vertical distribution of temperature, pressure, wind speed, composition, and so on at one place and at one time, but through the atmosphere of Titan.
Well, weren't the winds a bit different to what had been predicted? I seem to remember.
They were, and they were able to track the probe using Doppler measurements that were received by Cassini and then sent to Earth. And the upper atmosphere was a little more turbulent than they had predicted. The lower atmosphere not as turbulent, so this is why you go there, right?
I seem to remember that it took longer to descend through the atmosphere than they thought it was going to.
I think so. Yeah. We had just our models from what little we knew from Voyager and from ground base and Earth orbiting observations.
Yeah.
And I'll show you some of those in a few minutes as well.
Okay.
So this is just.
Sorry, I was going to say, and it all worked amazingly. It was a flawless descent.
Not only a flawless descent, but they pinpointed the landing 1.5 billion kilometers away. So in my way of looking at it, the real heroes of this mission are the people who understood the celestial mechanics of how things operate in the solar system and are able to guide this thing miraculously to a pinpoint landing. So the Huygens probe descended. It had a camera a downward facing camera, and we started to see now through much of the haze, started to see surface features. You can see what we used to call these fluvial channels or flow channels, and I think we were a little coy about calling them rivers at the time, but you can see valleys and mountain ranges and fluvial channels. And then in the lower right, you see a little more magnified image of the surface in black and white here. Clearly, you see the rivers. You can see the darker area on the bottom, that's hydrocarbon lake. And these little puffy things here are methane clouds in the troposphere.
Amazing.
And I remember being at Cornell University when I was working on this problem with Bob Samuelson. Carl Sagan was working on this problem, and a group from Canada, whose names I'm sorry I forget, were working on this problem of methane clouds in the atmosphere of Titan. We're all using the same data from Voyager 1 observations, and Canadian group said there are clearly no methane clouds. Sagan and Thompson said, yes, there are. And Bob and I said, I don't think we know yet. And it turns out there are. So the probe landed on the surface. We knew that the surface was probably had a collection of liquids on it. And we knew that from atmospheric modeling from the Voyager data, also from active radar measurements from Arecibo, where we bounced radar signals off the surface to see what the scattering profile looked like. And so Huygens was designed to not only land on a hard surface, but a mushy surface or in a lake. And it turns out that it landed in something kind of marshy. What you see here are rocks, probably water ice, covered with tholins, these atmospheric prebiotic chemicals, hydrocarbons and nitriles and so on that are falling down through the atmosphere. And then you see some smoother areas, which appear to be liquid hydrocarbons on the surface at the landing spot of Huygens.
And some of those pebbles, if you like, are quite rounded, aren't they? As if they've definitely been in some sort of liquid.
There is erosion on the surface, not only from liquid and atmospherics and so on. And there's they do not appear jagged at all. From the Cassini orbiter, they were able to take radar measurements of the surface. This is a false color image just to show detail. Well, I guess if you're doing radar measurements, you don't have any color, at least in visible part of the spectrum. But this just shows the a collection near the poles of lakes on the surface of Titan.
Are the lakes restricted to the polar areas?
They're not restricted to the polar areas. We see them at all latitudes. So,
right.
This is an interesting experiment that was done. This is called a radio occultation experiment. You can fly the spacecraft behind Titan, send a radio signal through the edge of the atmosphere and kind of pan down through the atmosphere. And then the Earth receives that signal, which is deflected at some angle and its intensity reduced at some proportion. And that observation gives you a quantity called temperature over mean molecular weight in the atmosphere and allows you to make temperature profiles. So the mean molecular weight is very, very close to 28, 2 times 14 nitrogen, diatomic nitrogen. And so we're able to get a temperature profile, at least for that location, showing how the temperature varies with height. And you can see here in this little graph that Titan has a troposphere just like the Earth does. It has a tropopause where the temperature turns over and starts increasing with height. And it has a stratosphere.
Fantastic.
I showed you the Voyager's infrared spectrum of the atmosphere. This is the Cassini infrared spectrum. This was taken by an instrument called SEERS, the Composite Infrared Spectrometer, aboard the Cassini orbiter. And so here we have much higher resolution data identifying all kinds of chemicals, and some of them building blocks for life, like hydrogen cyanide. And so we see this atmosphere that is mildly reducing, and it also produces somewhat of a greenhouse effect on Titan. As cold as the surface of Titan is, about 95 Kelvin, there's about, and I'm sorry I forgot to convert this, there's about a 38-degree increase in the surface temperature Fahrenheit from what it would be without an atmosphere. And this is caused by these chemical species that are asymmetrical, absorbing energy and re-emitting it back down to the surface, just like we have on Earth.
Of course, methane is an extremely potent greenhouse gas.
Yes, absolutely, and the primary volatile species in the lower atmosphere of Titan.
Sure.
From all of this, we're able to construct some models of what the internals of Titan might look like. And what I want to point your attention to here is that there is some indication that there may be a global subsurface ocean with liquid water, perhaps mixed with methane or other hydrocarbons. This is not a surprise, because when you fly a spacecraft by Titan and you measure the degree that its trajectory is modified by the gravity of Titan, it's not that much. And it equates to a bulk density of about 2 grams per cubic centimeter.
Right.
Earth is about 5.5 grams. So Earth is much more rocky. So we know there's a lot of water, either in liquid form or water ice, making up the composition of Titan. This is another image from Cassini showing a region where it appears that there's some cryovolcanism on the surface of Titan. This was suspected for a while, but here we have some observational evidence. Really exciting finding. Three images from the VIMS instrument on Cassini, showing all sides, all surface areas of Titan. Again, you see the darker areas as the lakes. You see the very whitish areas as clouds. You see surface areas as well as some, I guess these are, these are cloud regions. I'm not sure, in the polar areas.
Yeah, probably.
I just think this is a lovely image.
Beautiful. Look at that haze.
It's a bit colorized, but you see the red-orange atmosphere of Titan and the detached haze layer that we, as I mentioned, that we see on Pluto as well as Titan. And it turns out that I painted something that looks an awful lot like this about 30 years ago.
Really?
So I wonder if it was, prolific. This is one of my favorite images. Believe it or not, Cassini got this image just at the right time, just at the right angle to have sunlight reflecting off one of the hydrocarbon lakes on Titan and into the imager of Cassini. Just remarkable.
Is that reflection actually an image of the sun?
It is sunlight. It is sunlight reflecting off the lake.
Yeah, but that bright spot is are we looking at a direct reflection of the sun? That's amazing.
Oh, well, I don't know if that's, I wouldn't say that is an image, a spatially resolved image of the sun. I think that's a gradation in.
Yes, probably, yeah. But it's very bright, isn't it? Amazing.
Titan is an incredible world.
It is.
So this is an interesting place. It has water, liquid water, probably. Models indicate below the surface. It has a prebiotic atmosphere. It has lakes and rivers and seasons and winds and what do you want out of a body in the solar system? And so we're spending some more tax dollars, at least of the American tax dollars, to go take an even closer look. And this is the Dragonfly mission that will launch, I believe, in 1996. I'm sorry, 2026. 2026. I'm dating myself a little here. This is actually an octocopter. It will have 8 propellor systems that will fly it around through the atmosphere of Titan. Now, of course, we have a drone on the surface of Mars that's flying. Mars atmosphere being about 1% the density of Earth's. That's a tough ordeal. But the atmosphere of Titan, 50% greater surface pressure, no problem. And this drone, therefore, can be somewhat larger, and it's about the size of maybe a small school bus. It's rather large, with a RTG on the back end here, a radioisotopic thermoelectric generator, nuclear power source, and it is going to parachute into the atmosphere of Titan. I'll show you here in a minute. I'll go over some of the parts. It will have various instruments. Of course, it will have visual imagers and spectrometers and instruments to measure the winds and pressures and temperatures and so on at the surface of Titan.
Just one thing occurred to me about that. Are they at all worried that if it lands on the surface, it might actually freeze and get stuck to the surface?
Well, I'll tell you, in order to do that, you'd have to be able to liquefy water a little bit, right? Yeah,
true.
Water. That's not going to happen on the surface of Titan.
Yeah.
No, this probe is being developed by the Johns Hopkins University Applied Physics Laboratory, and believe me, they are taking the cold temperatures and what we know of the composition of the surface into account.
I'm sure they are.
The hope is that not only will they get more information about the solid surface and the atmosphere, but also the liquid surface. I believe there's a mass spectrometer on board that's going to be able to tell us more about the composition of all 3 of those.
Any idea how long they're expecting Dragonfly to last?
Well, let's see. I believe I have to check. I believe the planned mission on the surface is 2 years.
2 years.
Earth years. Earth years. Um,
Earth years, yeah.
but I imagine almost everything that we send up now is far more durable than its planned lifetime.
Sure.
And so it's not unusual. In fact, I think it's almost the rule that we send up missions that that exceed their lifetime, and we ask for extended funding, and we get that. And if you just look at the Voyager missions, you can understand what that's about. Let's see.
It must be so incredibly hard to design a vehicle that's going to work in those low temperatures and work reliably.
I suspect. I was in Barrow, Alaska a number of years ago, and I remember it was hard just to get my my cell phone operating in
Really?
20 and 40 degree below temperatures. Let's see. So 2 years is not a correct number. I think it's more like 2 months.
2 months, right?
Or for the initial planned mission.
Right.
Sorry.
But as you say, it'll, if past experience is anything to go by, especially with the MERs, then it'll probably last a lot longer.
Right. Just a indication of how it plans to get there. Many gravity assists. That means you don't have to have as large a booster, and you can do this more energy efficiently. It will begin aerobraking through the atmosphere of Titan, and then it will open a parachute that will slow it down until it's able to drop its heat shield. And it's actually going to just drop this thing in midair, and its rotors will begin operating, and it will fly itself to its surface. And remember, we're 1.5 billion kilometers away, so we're not using a joystick to do this. So it has it has sensors, and it has intelligence that's going to be able to pick out a suitable landing site. I think in real stream this cannot play. Okay, right. So this was a video of releasing the Dragonfly probe.
Oh yes, you'd have to show your screen for that, unfortunately.
Right, and so it will copter itself down to the surface, raise its communication antenna. It will be able to receive signals from the Earth over long periods of time. It will send up science packages to tell it what we'd like it to do, and then it will fly off and look for a suitable landing site. And it will actually be able to fly a little bit further. It does this kind of hip-hop motion where it flies beyond that site, looks for other landing sites, comes back to the original site, and then does that same kind of progression again.
Right.
And I think that is it.
Totally autonomously.
Mm-hmm. Totally autonomously, that's right.
Amazing, amazing.
Yep, that's it.
Right. Well, thank you so much, Lou, and I hope viewers you've enjoyed that look at that fascinating world Titan. And yes, thanks, Lou. That was absolutely fantastic. So there you are. That's Titan. And as I said, this is the first in a series of Moons of the Week. And what would you, our viewers, like to see in this series? If you've got a moon that you're particularly fond of and you'd like to learn more information about, then pop it in the chat now, and we'll see what we can do. So as for next week's moon, we need to discuss what we're going to tackle next week. But I can guarantee you it'll be interesting because
button moon.
Yes, okay. Yeah. Right, don't give up your day job. And
Steve's got a question in the chat now. I don't know if anybody can help him with that. What happens at the end of mission? Will the power generating device remain on Titan for good? Is there a danger of polluting?
Well, the mission will remain on Titan. It's not coming back, and so its RTG will remain with it, and it should be. It is well contained. I think the prospects for pollution are very slim. You might remember that the Cassini spacecraft also flew to Saturn with an RTG, and it did a number of gravity assists before it got there, and one of the gravity assists was with Earth. And so there were some environmentalists who were very concerned about what happens if it kind of misses its trajectory and hits Earth's atmosphere, and this radioactive material gets in the atmosphere and kills us all. And the truth is that this stuff is packed very tightly. And my understanding is you can put a string of dynamite around these RTGs, this plutonium, and blow it, and you won't see any degradation. So it's the opportunity for pollution on Titan, I think, is very, very low.
I mean, they drop these RTGs out of planes at 50,000 feet, and they survive. So they are designed not to break open.
They're baked into ceramics, actually.